Okay, hello everyone. So in this video we're going to be going over 2019, all the capacitor questions in the exam papers from 2019. So we're going to start off with May 2019, time zone 1, and the capacitor question looks like this. We have a student is making a parallel plate capacitor given capacitance C, 68 nanofarads, and what he's doing is he's got 2 sheets of aluminium foil and then inserting 1 sheet of plastic film between them. We know the width is 450 millimeters, and we know the thickness 55 micrometers, and we're given the permittivity epsilon. And we have to calculate the total length of aluminium foil that the student will require. So the total length, since we have 2 sheets, we probably have to take that into account, but we're definitely, first of all, just finding the length of these sheets. We already know the widths. Okay, well, we have to remember that we have this capacitance formula that C is epsilon area over D, the thickness between the plates. And since we know C, epsilon, and D, the thickness, we can work out what the area is. So let's just do that. And what we get here is something along these lines. So plug that into your calculator. So that's the area, and of course that's width times length. So the length is going to be the area divided by the width, which is 0.450 meters, and then you get roughly 0.33 meters. So that is 1 length, but we need 2 of those sheets, so the total length is going to be 2L, which is around 0.66 meters. Okay. Next one is that the film begins to conduct when the electric field strength in it exceeds that amount. So we don't want the plastic film to conduct. We want it to remain a dielectric, which is an insulator that can just be polarized. But of course, if you just apply a strong enough electric field, then pretty much all materials, they can conduct. We have to calculate the maximum charge that can be stored on the capacitor. Okay. So we're given an electric field strength, meganewtons per coulomb, and we know that the electric field strength between 2 parallel plates is the potential difference divided by the distance between the plates. But we also know that the voltage on a capacitor is Q over C, charge over C. So we can plug that in like this. And to find the maximum charge, we just have to plug into this equation and find Q. That will be when E is maximum, we get the maximum charge, and D and C are givens. So what do we get? We get 1.5. -6 micro, and then what am I missing? The C, the capacitance, which was 68, right? And that should give this coulombs. So that C is coulombs, not capacitance. Okay. Then we have this this problem now. Okay, so we can discharge the capacitor using this circuit. got a 12-volt battery over there. What did we have before? Oh, that was just making the capacitor. Now we're going to put it in a circuit. Okay, so if we have fully charged the capacitor, and then we start discharging it through a 1.2 kilo ohm resistor, time taken for the charge to fall to 50%. Okay, well, we know that charge drops exponentially like voltage, so we can write down that if you want. Charge is the initial charge, which we maybe sometimes call capital Q, e to the minus t over the time constant RC. If we want the charge to be half of the initial charge, so I want Q of t to be half big Q. So I basically have this equation where I just need to solve for t, and we can do that relatively easily. Just take ln on both sides, and then work out what t is. It's going to be minus RC ln 0.5. And that's going to be, let's see, minus, and the R is 1.2 kilo ohms. Capacitance was 68 nanofarads. And that gives us this in seconds. Okay. Now the ammeter is replaced by a coil. So now you have to imagine that we suddenly have a metal coil over there that the current can run through. Explain why there will be an induced EMF in the coil. So this is of course Faraday's law, induced EMF. And why we're going to get an induced EMF when it's discharging. Well, we know as it discharges, we know the current is going to start off being maximum, and then the current drops to 0. So we have a changing current through the coil, and the current is decreasing through the coil, and therefore, we know that currents produce magnetic fields, magnetic flux through the coil. So that magnetic flux is also going to be decreasing, and hence we are going to have an induced EMF created according to Faraday's law because we have a changing flux. So we try and write something along those lines. As the current decreases, the magnetic flux through the coil changes, decreases. Can maybe say decreases since we're hence an induced EMF is created in the coil according to Faraday's law. It's always good to name drop Faraday's law in these questions, right? Okay. Suggest one change to the discharge circuit apart from changes to the coil that will increase the maximum induced. So to increase the maximum induced EMF, we want, say, a more rapid change in flux. So for instance, we want the magnetic flux to decrease faster. And in order to do that, we could, for instance, lower the resistor, because then we would have a then the time constant t. The time constant is proportional to r, and if we were to decrease r, then the time would also decrease. So it discharges faster, and we get a larger induced EMF. So that would be one way of doing this. So lowering the resistor will discharge the capacitor faster because we know the time is proportional to R. Hence, the magnetic flux in the coil will decrease faster, and the max induced EMF will increase. Okay, that was main 19 time zone 1. Then let's move on to main 19 time zone 2. So here we have this problem. It starts off as a sort of a normal topic 5 electric circuit question. So S is initially open. We have these light bulbs identical with a resistance of 4. Cell is 12. No internal resistance. So calculate the total power dissipated in the circuit. Total power. Okay, well, when it's open, the switch is open. So we're basically just looking at Y and Z. Total resistance is 8. So of course the power dissipated is just this, V squared over R total. And 12 squared over 8 gives us 18 watts. Switch is now closed. Why will the current increase? Well, when we close the switch, we sort of create this parallel combination. So we have the same PD across Y and Z because nothing has changed there. So you get the same current through Y and Z, but we get an additional current flowing through X. So the total current has to increase. So same current through YZ, same PD across those two, but more current, or additional current, but additional current now flowing through X. Okay, so the total current will increase. The ratio of the power dissipated in Y only with S open and S closed. Well, not really much is going to change when it comes to Y, because Y will always have the same PD because it will share the PD. Because Y and Z are identical, we're always going to have 6 volts across Y. Regardless of whether S is open or not. So this ratio is just going to be 1, and we can maybe stress that by saying that there will always be 6 volts across Y. Hence, the ratio will be 1. And quick calculation, right? Well, we don't even have to do that, I think. Always be 6 volts across Y, and we have the same power dissipated. Okay. Then we have a capacitor. Capacitor gets involved here. So the cell is used to charge a capacitor in vacuum, epsilon naught. And then we connect the capacitor to an ideal voltmeter. So it's no longer connected to the EMF. No longer connected to EMF. That's an important thing to know, because then we know that the charge is going to be constant. Charge is constant. So the capacitance is that reading. So we know the PD across the capacitor. Energy stored. Okay, so relatively easy question because there is this formula, half CV squared in the data booklet. We have 6 micro. Did I say nano before? I meant microfarad times 12 squared, and that gives us something like 4.3 10 to the negative 4 joules. When it's fully charged, the space between the plates is filled with the dielectric with double the permittivity of vacuum. So we are doubling the permittivity. And how does that change the energy stored? Okay, so now it's important to know, we know that the capacitance is proportional to epsilon. So if we double epsilon, then we are doubling the capacitance. Okay, so the new capacitance is going to be 2 times the previous one. So we can, for instance, work out how does the voltage change then. And because we have the same amount of charge, right? So we know that voltage, the new voltage is the same amount of charge because it's not connected to an EMF. It can't gain any more charge over C prime, and we know C prime is 2C. Q over C was the previous voltage, so the voltage has halved by doing this. So the new energy is half C prime V prime squared. C prime is 2C, V prime is 1/2 V squared. So what's that going to give us? It's going to give us well, that cancels out, but then we get 1/4. That's going to be 1/2. How should I do this? 1/2 times 1/2 C V squared, and we can see half C V squared was what we had before. So we're going to have half of what we had before. So that is, of course, what's that? 2.15, right? Times 10 to the negative 4. And then we're looking for the change. So the change in energy says calculate the change in energy. And that is going to be then rounded off to 2 sig figs, 2.2, 10 to the negative 4 joules. And this is energy has been lost, right? So the change is kind of negative. Okay, lost energy. The capacitor lost energy by having this dielectric inserted between its 2 plates. Okay, and then we have to sort of suggest, what's the cause of that? And that is because when a dielectric sort of gets inserted, the field actually pulls the dielectric in slightly. So the electric field does positive work. The electric field does positive work on the dielectric material, so that the electric field that is storing the energy loses some of its energy. And this is quite sort of an abstract detail that they've included in the syllabus. The electric field in the capacitor does work on the dielectric as it gets pulled in slightly. And therefore the field loses energy. So the electric field does work on the dielectric as it gets pulled in slightly. Hence, the field loses energy. Okay. Then we come to November 19, and we have this question, which was a little bit tricky, especially the question B. So we have 2 capacitors shown like this, not connected to an EMF. So there's no EMF in the circuit. So again, that sort of implies Q, total charge, is constant because they can't really go anywhere, and you can't gain new charge from an EMF. So we have a capacitance over here, and excess charge on one plate. Okay, and we know that the charge here is 48 microcoulombs, and then we have uncharged capacitor C. Okay, calculate the energy stored in X. So this is an easy one again, because we just have to use this formula, and we know that V is Q over C. Okay, so we know the capacitor, we know the charge. So I'd rather write this equation as half q squared over c, and that is going to be 1/2. Charge is 48 microcoulombs, square that, and we have 18 10 to the negative 6 is the capacitance, and that should give 6.4 10 to the negative 5 joules. Okay, then we come to the hard one. Capacitance of Y is 12 microfarads. Okay, S is now closed. Okay, so a current can flow. Now Y is uncharged, X is charged. So X kind of acts like an EMF. It can pump charge around, but we can't gain or lose charge. It's just the charge will run onto Y. And of course, as the current flows, some energy is going to be dissipated in the resistor R. But calculate the final charge on X and the final charge on Y. So we can basically start off by understanding that you get sort of this an equilibrium situation. Steady state occurs when the voltages are equal, because then the current will stop. Okay, and that if the voltages are equal, then we have a new charge on X. Let's call that QX over the capacitance of X, and then some charge has now been gained on Y. So we have this equation when the voltages are equal. Okay, so that's one equation with two unknowns, but we also know that no charge has been lost, so that the sum of those two charges is the original charge, the 48. Let me just call this one up here Q now, because I have another QX down here. So Q is 48 microcoulombs, so they add up to 48 microcoulombs. So two equations with two unknowns. So what do we do here? Well, I believe we simply just solve them, do the math, right? We can multiply by CX, and then we can sub in QY, 48, let's just work it out. That's in microcoulombs minus QX. And then we can sort of solve for QX, right? We expand, and let me see, what did I do here? We can also just plug in the numbers, right? So CX is 18, CY is 12, and then we can expand the bracket. And then we add all that over on one side, and you can do the math. So if you just do the math, you don't have to show the steps. You get 28.8, which is around, so round that off to 29 microcoulombs. You get 19.2, which is 19 microcoulombs. So yeah, that one was a little bit tricky. Then we have to calculate the final total energy. Okay, so after we close the switch, what's the total energy now? And we can do that by just adding the two energies for the capacitor. So we have a QX over CX, a voltage on X squared. We have a CY, QY over CY squared. And then we have to simply plug in all those nasty numbers. 28.8. I'm using 28.8 now instead of the 29. That is being squared, and then we have 18 10 to the negative 6, and then 19.2 10 to the negative 6 squared over 12, and then we end up with 3.8 10 to the negative 5 joules. So some energy has been lost compared to, we had 6.4 10 to the negative 5. Now we have 3.8. So some energy has been lost. And as we mentioned before, that's because the current has run through the resistor and some energy was dissipated there. And that is what we have to write here, suggest why they're different. So energy was dissipated in R as the current flowed through during the charging of Y. One capacitor charged the other. There you go. Okay, see you next time.